Hey, everybody. So we're going to start talking about the topic of probability today. And we're going to really just start with mostly a bunch of terminology. We'll do a few examples and get a few ideas of some computations we can do, but we're mostly laying down some terminology today. And then in the next several videos, we'll start actually banging out some numbers and computing probabilities and so forth. But let's set the stage first for what this stuff means. Let's give our foundation for all this stuff. Okay, so let's start with the word probability, right? So we've been doing videos on statistics. We're shifting into probability now, and we're going to see these two topics come together later. So we're kind of shifting gears here for a bit. So what is probability? So it's tricky exactly to define probability without getting super technical. So we're going to kind of give ourselves a nice intuitive understanding of what we mean by it. We can think of it as our measure of certainty of how an activity or experiment will turn out. Okay, so it's just an idea of how sure we are about something that will happen. And let me define the term experiment. Right, we're just going to think of this as a process. Sometimes we'll call these trials. A process determined by chance. Okay, again, we could get some more technical definitions, but these are going to be good enough for us right now. Right, it's things that we don't know exactly how they're going to turn out when we start them, right? We'll do an example of all these. I want to finish the first set of vocabulary so that we can kind of look at them completely together in a couple of examples. We will call an outcome is the result of an experiment. Okay. And the sample space is the set of all possible outcomes, right? All the things that could possibly happen when we begin an experiment. And then our last vocabulary for now is an event. This is some combination of outcomes, right? Including just one of them, right? So we'll have all these outcomes in our sample space, and any single one of them is an event, or sometimes a couple of them together can be an event. So let's use examples to make these definitions clearer. So I'm going to start. Let's use the example of where our experiment is tossing a fair coin 3 times. Okay, and what I mean by fair there is each side has the same likelihood of coming up. So when you toss a coin, right, this is an experiment. We don't know whether it's going to be heads or tails when we toss the coin, right? It's determined by chance. So in this case, our experiment is just what I've said, tossing the coin 3 times. The outcome, we won't know until it happens. Okay, this is just going to be the result of the experiment. Okay. But what we can write out is the sample space. Okay, The sample space, remember, is the set of all possible outcomes. So what could happen when we toss a coin 3 times? I'll use H and T to represent what could happen. This is one outcome. So remember, our experiment is flipping a coin 3 times. So when we're done, we'll have tossed it 3 times. So one possible outcome is I got heads all 3 times. Okay. Another possible outcome is I get heads twice and then tails. Or maybe I get heads, then tails, then heads. Or maybe I get tails first and then heads twice. Maybe I get tails twice first. Maybe I get tails, heads, tails. Maybe I get heads, tails, tails. Or maybe I get tails, 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 right? This is our sample space. These are all the possible outcomes, right, from this experiment. I want to be very clear. Each collection of 3 results here is one outcome because our experiment is tossing the coin 3 times. So flipping heads the first time is not an outcome of this experiment. Okay? It is an outcome if the experiment was flipping a coin once. But we're flipping it 3 times, so all of these are our outcome. All of this is our sample space. Each triple, each collection of 3 results is going to be a single outcome. Let's make an event. Let me grab another color for this. So we often name events using, there's a few ways we'll name events. Sometimes we just write them out. I like to give them a name, like let's call A, the event we flip heads first. Okay, so remember, an event is some combination of outcomes. Okay, this event is flip heads first. There are 4 outcomes in this event, right? This is the combination of outcomes for this event. Okay, we could have another event, let's say flip 3 tails. All right, I'll mark this one with a star. So this one is our little circles. This one is our star. Oops. Okay. There's only one outcome in this event. Okay. So an outcome, even though it says combination of some combination of outcomes, we include the possibility that the combination is just a single one of them, right? So these are both events for us. Okay. Let's do another quick example, another kind of typical experiment. Let's say I were to roll 2 3-sided die. All right, so I have a pair of dice, and each of them has 3 numbers on it. We'll say 1, 2, and 3. So that's my experiment. Let's write out the sample space here. Okay, so again, just like this, the sample space is the total experiment, the outcome of the total experiment. When I roll 2 dice, I'm going to get 2 numbers. So I could roll, I'm just going to write it this way, where I'm just kind of writing what's on each die. So I roll a 1 and a 1, a 1 and a 2, a 1 and a 3. Maybe I roll a 2 and a 1, a 2 and a 2, a 2 and a 3, or a 3 and a 1, a 3 and a 2, a 3 and a 3. Okay. Again, there are 18 numbers here, but there are only 9 outcomes because each pair is one outcome of the experiment of rolling these 2 3-sided die. Okay. And just like with tossing the coin, we can name events from this. Let's try E is the event. Roll the same on both die. Right. So in that case, we're talking about these 3 outcomes. All right, that's our combination. Or maybe let's do another event. I'll call it F. Let's say the second die is greater than the first, right? So I'm assuming that I've kind of numbered the die. One's the first one, one's the second, and I've written them in the order. So I'm just looking for all the outcomes where the second number is bigger than the first. I'll mark these with filled in circles. And it looks like we just have these three, right? Where the second die is greater than the first, okay? So there are we've got a whole bunch of stuff happening here. Experiments, outcomes, sample spaces, and events, okay? However, we skipped right over probability, right? Our first vocabulary term. I haven't really talked about it. Actually, let's hold off on it one more second. I want to make something clear before we get to that. Let's think about one more experiment. I won't write anything down because it's a little bit trickier. Another experiment we could do would be, it was raining yesterday. Maybe I take a cup and I set it out in the rain for 10 seconds, right? I don't know how many drops of rain are going to fall into it. Rain kind of falls all over the place. And so the experiment could be how much, measuring the volume of water in that cup after those 10 seconds, right? I can't write out the sample space for this, at least not in this way, right? How much rain could be in there? There could be none. None could go in, right? I could set it in a spot that doesn't get a raindrop for 10 seconds, right? It wasn't raining super hard. If you looked at the ground, there were spots that were still dry. So maybe I set it and no rain goes in it. Or I could set it in a spot that happens to get a bunch of rain in the next couple of seconds, right? Several drops go in. So anywhere from 0 to, I don't have a good metric for volume, but right, 25 drops maybe could fall in 10 seconds, and if it picked up for a second, right? Every once in a while we get these little bursts of heavy rain or something like that. Also, I'm not measuring in drops because that's not a normal specific amount. I'm measuring volume, so maybe I'd be measuring in milliliters, right? And so I could have, each drop could be a different number of milliliters. I could have anywhere from 0 up to who knows how many milliliters or in a drop. I don't have a good sense of that, but anywhere in between. There could be 10.735 milliliters or 12 milliliters or 12.9999972 milliliters, right? Depending on how accurately we measure. In other words, I can't write out each option. There's an infinite number of options, right? And so it's a very different kind of sample space, okay? What we might notice is there are a discrete number of things that can happen in each of these cases. Our outcomes in some sense are discrete versus continuous, right? We had talked about discrete versus continuous data earlier in the quarter, right? If I thought about here, maybe I could think of this as the number of heads. That can only come as 0, 1, 2, or 3. I don't know why that was hard for me to count there. Right, those are discrete numbers versus the volume of rain could be on a spectrum, right? An infinite number of values between 0 and some upper limit of how much rain could possibly fall into that cup, right? And even if it was only up to 2 milliliters, there's an infinite number of measures of volume between 0 and 2 milliliters. So we can't write out sample spaces in this way. We will learn to deal with continuous data, but we're mostly going to not think about it or think about it too hard for now. And the stuff that I ask you to do sort of more explicitly where we're writing out sample spaces and stuff, we're going to stick with discrete kinds of things for the most part right now. And then we'll definitely get into continuous stuff because continuous stuff gets pretty interesting, right? When we want to study humans and our behaviors, a lot of it, things like our heights and weights, lung capacity, all these kinds of things are on continuous spectrums, and so we need to figure out ways to handle those kinds of things. Okay, so now let's use these sample spaces that we just created. Actually, maybe I'll redraw them so we have clean start to discuss the next thing, which is, well, to go into more detail about probability, okay? So we said probability was a measure of certainty about the outcome of an event. We also sometimes think of it as the long-term frequency, long-term relative frequency of an event. Okay. So, for instance, we'll come back to these in a moment. Let's just talk for a second. If I was flipping a coin once, I think we all have the idea that we would say, what's the probability of getting heads is 50%, meaning I'm half sure I'll get heads. Sometimes I expect that half the time I flip a coin I get heads, half the time I get tails. So if I was going to flip a coin right now, my certainty that heads will come up, I would call it 50%. Okay. Another way to think about that is when we say the probability is 50%, another way, and there's different schools of thought on which one of these is the more correct way to think about it. We're not going to get into that. But another good way for us to think about it sometimes is if I continued to flip a coin over and over and over again, in the long term, I would expect to get about half heads. So if we flipped a coin 10,000 times and we took the number of heads divided by those 10,000 flips, the relative frequency, we would expect it to be about 50%. And the more we do it, the more we expect that to be true. So let's take a look at this idea for a second. We'll come back to this a little more in a moment, but this is a good moment to see it. Here is some data back from when I got to meet classes in person. I had students flip a coin. So if you should be able to see this. I've got these columns of heads and tails. So I had students flip a coin 12 times and they wrote down how many heads they got. And so I have this data of all these coin flips, right? If you look closely, you see somebody here, for instance, this person got 11 and 1, right? Somebody else here got 2 heads and 10 tails versus 11 heads and 1 tail. So sometimes you flip a coin, you get a bunch of heads, sometimes you get a bunch of tails. But let's look at the long-term frequency. This histogram shows us, so I've got, what is this, over 2,200 coin tosses here, right? About 2,260, just about, 2,256 coin tosses. And it's pretty much half and half, heads and tails. The blue is heads, the red is tails. It's not perfectly half and half, but it's pretty close, right? This number here, 0.5072, that's the relative frequency after all these coin tosses, and it's pretty close to 50%, right? So this is another sort of notion we're going to have about what probability means. Okay, and we'll have some notation for it. Okay, and then we'll compute some using those sample spaces and experiments we just looked at a moment ago. So here's our notation. Let's let E be an event, right? Just giving it a name. Then the notation, or we write P of E to mean the probability that event E occurs. Okay? All right, so this collection of symbols, this whole collection of symbols, P parentheses, E parentheses, represents some number, right, that we're going to try to compute. And that number represents the probability that event E occurs. Sometimes you'll see people write things like, what's the probability of flipping a head? Sometimes people just write the event in there, and we still mean this, the probability of this event happening, right? We just talked about this one. I expect heads to come up about 50% of the time. A little later in the quarter, we'll introduce notation. I'm going to mention it here. We're not going to use it much at all now, but we will use it much later. We're mostly going to stick with these two notations for now. Either I'll name an event and write P of E, or whatever name I give the event, or I'll just write it out if we're only doing a quick thing with it and I don't need to take the extra step. This is usually preferred. It keeps our work a little bit neater, but if we're only going to use an event once, sometimes we just write it instead of going through naming it. A little later in the quarter, we'll do things like let x equal, let's say, the number rolled on a 6-sided die, and then we might write something like P of x equals 2, and this symbol will be the probability that the number rolled on a 6-sided die is 2. Okay, and we'll talk about how to compute that later. But I don't want to worry too much about this notation right now, but just since we're talking about notation of events, it will come up, and we'll do a little more detailed work with that when we get to that. So for now, we'll name events with letters or write them out in totality. Okay, so let's, well, a couple of things I want to say about probability. I keep saying we're going to get to those sample spaces, and remembering there's a couple of things I want to do. I've kind of hinted at this idea. Probability is going to be a number. It's measuring how certain we are of something. And the number is always going to be between 0 and 1. Okay? If a probability is 0, this means it's impossible. If a probability is 1, it means that event is certain. It has to happen. Right? And if a probability is some number in between, like we did, the probability of flipping a head was 50%, then that tells us this is, we're half certain it's going to happen, or we expect it to happen about half the time, right? It's somewhere in between impossible and certain, right? Right. So for instance, if my experiment was flipping a coin and I said, what's the probability that I flip the number 7? That's impossible. My coin has heads or tails. I can't flip it and it becomes a number 7 somehow. On the other hand, my event could be, I flip a coin, what's the probability it lands? Right? Well, it's going to land. That's certain. And so we could say the probability there is 1. And so that's the idea of impossible and certain. But most things we care about will be in between these two numbers, typically, right? All right, so let's start talking about computing some probabilities in the easiest cases. Okay, so there we go. We're going to stick right now with experiments where all outcomes are equally likely. Right? Each possible outcome in the sample space, everything we write in the sample space, has the same probability of happening. Okay, so flipping a coin is 1. If I flip a coin 1 time, the sample space is heads and tails. And they both have the same chance of happening. So we'd say those are equally likely. Or when we roll a die, each number should be equally likely to show up, right? If the die aren't rigged somehow, right? When this is the case, the probability that event E happens is the number of outcomes in event E divided by the number of outcomes in the sample space. Okay? you can see why this is starting to feel like relative frequency. How many times did the thing we're interested in happen divided by how many total things are there, right? Remember, relative frequency was you counted up, we were dividing into classes, and we would say how many data points are in this class divided by the total number of data. Well, now it's like our events are our classes, and the sample space is the total number of data points, right? It's a similar idea, okay? All right, so let's look back at those experiments we did a moment ago and use this. Let's start with the flipping a coin 3 times experiment. And remember, I had this sample space. This is a case where we assume all of these outcomes are equally likely. All right, so each time we flip the coin, heads or tails are equally likely, so we expect when we flip it 3 times, each combination is equally likely. Okay, so if I let's say E equals the event more tails than heads, then the probability of event E is the number of outcomes in E divided by the number of outcomes in the sample space. Okay. So more tails than heads. Well, 3 heads, no tails, 2 heads, 1 tail, 2 tails, 1 head is all these, 3 tails, no heads is that one. So we have 4 outcomes in event E. There's a total number of 8 outcomes in the sample space. So we get 1/2 or 0.5. Either of these fractions is fine. And really, I don't actually always reduce fractions when I'm dealing with probabilities because sometimes they show us something. In this case, it's showing us that there are 4 out of our 8 outcomes in E, right? But notice when it's a sample space like this where each outcome is equally likely, we're just counting. It's pretty straightforward, right? Let's do a couple of things. Let's do one more example. Let's look at an example like F equals flip heads 4 times. Right. So the probability of F, well, this is a silly example. There are no outcomes where I flip heads 4 times. There are still 8. 0 divided by 8 is 0, right? Just showing you what happens, how this works out with that idea of impossible events. The smallest this number can be, the 8's never going to change, and when we're counting outcomes, there's never going to be less than 0. I can't have negative outcomes. In a similar way, let's do one more silly event. Let's have G be the event flip heads or tails at least once. All right. Well, every outcome has heads or tails at least once, right? This one has heads at least once. This one has tails at least once. This one has both of them at least once, right? So in other words, there are 8 outcomes out of our 8 that satisfy this event. It's certain to happen, probability 1. And now you see why probability can't be larger than 1, because you can't have more outcomes in an event than there are total number of outcomes, right? And so the best case scenario here is 8 out of 8, right? And the worst case scenario is 0 out of 8, okay? So impossible, certain, somewhere in between, okay? And that is our idea of probability here, okay? This again is something we won't be able to do when we're talking about continuous data. We won't be able to count this way, right? You can't count up how many possible birth weights are there. There's an infinite number of birth weights that are possible, so we can't count that. and do the same thing. So we'll have to develop some more sophisticated methods for that stuff, but we will get to that a little bit later. Let's mention a couple of other things. I kind of hinted at an idea already, something called the law of large numbers. This just says if we repeat an experiment, or as the number of trials increases, the relative frequency in an experiment tends towards, let's call it, the theoretical probability. Right. So this was, I was hinting at when we looked at that data from flipping coins. Let's go back to that for a second. Right. So again, let me highlight this, that in 12 flips, you get things that are very far away, very different than 50-50, right? We all expect, we'll call that our theoretical probability. We expect that a coin will get half heads, half tails. But we know if I flip a coin 4 times, I might not get 2 heads and 2 tails. I might get 4 heads in a row, right? That can happen in the short term. But what we expect is as we tend to go further and further on, conducting more and more experiments, we start to get closer and closer to that, that theoretical probability. And that's what we saw here, that after these more than 2,000 coin flips, we were at really close to 50% heads and 50% tails, right? And I expect that when I do this more and more with more students, we'll tend to get closer and closer. Doesn't mean we always get closer, right? The next person who flips a coin for me might flip it 10 times and get 10 heads in a row. And all of a sudden the heads frequency gets a little higher. It's already a little higher than 50%, it could get a little higher. But if I conduct this another 100 times, another 1,000 times, overall we'll tend to get closer and closer towards that 50%. If you look at this column here, let me blow this up a little bit. This column E is keeping track of the relative frequency as we go along doing this experiment. So after the first person flipped a coin, they had about 58% heads. By the time we got down to the 6th person, right, it had actually gotten worse. There was a bunch of people who got a lot of heads in here. And so we were up to 68%. But then after a few more people went, we were back to 58%. Then you can see it's getting closer to 50%, 52%, 52%. Here it got a little bit worse again. There was a run of a bunch of heads and we jumped up to 53%, then back down to 52, and then we hit about 50%. And that's where we are at this point, 50.5013, right? Oh, I guess this one up here hasn't been updated for the last set. So after another set of people did this, we're closer to 50% than we were before, right? Looks like I have a little data to add to those charts up there. And that just hammers home the point a little bit more, right? We're getting closer and closer to 50% as we go on. Usually, once in a while, right, the next person could have a string of heads and we go a little further away, but we tend to get closer and closer to that theoretical probability. Let's look at one more set of data. This is another thing I've done with students where I had them conduct an experiment in class. Let me show the data I want to show. So in this experiment, there's a few things going on. I had a little bag for somebody who doesn't play Dungeons and Dragons. I own a surprising number of dice of various sizes, right? Dungeons and Dragons uses all these, like, 18 and 20 and 21 sided die or something. Anyways, I've got a bunch of them that I ordered to do probability experiments. And one of the ones I do in class is I pass around a bag that has 5 dice in it. I think they're all 20-sided die. Oh no, these ones are just 6-sided die. But anyways, they're also different colors. There's a red, a blue, a yellow, a purple, and a green, right? These 5 colors. And so, the experiment I have my class conduct is each person reaches in and pulls out 1 marble and then rolls it. So their outcome is 2 things. Sorry, not marble, die. The color of the die and the number that they rolled. Right now, I only want to think about the color, okay? We would expect, if you're reaching into a bag and not looking, each colored die has about the same probability of being pulled out. We would also expect that the number rolled also has the same probability of being pulled out, okay? So this histogram I'm looking at here is the distribution of numbers that are rolled, right? So this first column is the 1s, 2s, 3s, 4s, 5s, and 6s, okay? And what we see is that they're not exactly the same number of 1s as there are 5s and all of these different numbers, but they're getting close to something even, as we expect, right? I haven't done that many rolls. I've got to update some of this. I know I have more data, but we still see the idea. Similar thing here. Here's a frequency table for the colors that are pulled. Something interesting has happened there, though. If you notice, let's blow this up. If you notice, the red has been pulled out 115 times, the blue 114, the purple 111, the yellow 115. This is what I expect, that they're all going to be pulled out about the same number of times. And suddenly the green is about 30 pulls behind. That's a big difference, right? And my explanation for this is that most likely in one of the classes, and this happened recently, these numbers used to be even, and I didn't notice this, I didn't collect all this data, I have a piece of paper and people write down everything and then I enter it after class. I suspect that whoever, one of the first people to pulled a green and never put it back in the bag. And then at the end of class realized they still had it and put it back in the bag when it was being passed around, but didn't tell me that it had been left out. And so greens didn't get pulled at all. Maybe this happened for a couple, or maybe I lost it and it was in my office for a couple classes. Clearly something happened. This is too big of a difference. This is what we would call an outlier. When we see these other 4 data points are all very similar, and then this one is drastically different, right? 30 times below the other ones. You know, that's like a 30% difference, more or less. It's pretty big. So in any event, I think this illustrates 2 good points. It does seem like the law of large numbers was happening, that we were getting approximately even frequencies of all of these, except here where something happened that probably means this is an outlier. There was some experimental error in that data, right? So if I look down this chart on the left where I've kept track of all the colors, if I'm careful, I can probably find a place where we see no greens for a long, long time. And that could be, right, it's looking like right here, we see a green, and then I don't see green again until here. My guess is that's a class where somebody held the green until the end, not intentionally, but then, and didn't tell me, and so it was back in the bag. I didn't notice anything different. And if I exclude that set, which I'll probably do, I should probably find much more even numbers after that. Okay, so that is our law of large numbers. And let's end this one here. I think that's enough. There's a few more ideas. I'll make another video on those. We've covered a lot in this one. All right, thanks everybody.